Before we learned about derivatives, we learned something called the limit process, which was the longer way of doing a derivative, but it was the definition of a derivative and told us what it meant to take the derivative of something. And for integrals, integrals have the same story. Integrals have this definition of an integral, and it tells us what it means when we integrate something. This equation is made up of f of c sub I times the change in x. Now this looks scary at first, but all this means is that we're going to take the height and the base of each rectangle and multiply them to find the area. So looking at the first graph on the left, the f of c sub I, that's the height of the rectangle at c sub I. I is just the number of term that you use, and it changes as we calculate the height of each rectangle. For instance, the I here, this is the first term, this is the second I, this is the third I. I is just the number of terms, the ith term. And f of c sub I will give you the height, and the change in x will give you the base. And we know that to calculate the area of a rectangle, you take the height times the base. Area is the height times the base. And that's where we get f of c sub I from. F of c sub I is the height, and we'll multiply that by the base. And we're pretty much going to do that for every single rectangle and add them all up together. That's what this summation symbol means. Summation is just going to add up all these rectangles to find the total area underneath the curve. And over here on the left side, you can see that we have 3 rectangles versus 4 rectangles on the right side. The rectangles is represented by the letter n. N is the number of rectangles. And on the left, because our n is 3, and on the right our n is 4, you can see that the blue shaded area is all the space that's unaccounted for. When we're calculating the area of each rectangle, we're not calculating this blue area. And as we have more and more rectangles, that blue area becomes less and less until we've got a number that's really, 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 really close to the actual value of the area underneath the curve. And that's what our limit as n approaches to infinity represents. As the number of rectangles increases almost towards infinity, as the number of rectangles increase towards infinity, that blue shaded area becomes less and less until we have an answer that's really, really, really close to the actual area underneath the curve. So again, going over our limit process equation, the limit as n approaches to infinity represents the number of rectangles. And as we have more and more and more, our answer becomes more and more and more closer, more and more close to the actual area of underneath the curve. Again, the f of c sub I times the change in x, that's going to be the height times the base of each rectangle. You're going to take the base times the height of each rectangle and add them all up, add all of them up, and that's what the summation is. The summation is just adding up the area of each rectangle. And I can't really draw an infinite number of rectangles, but if we do have an infinite number of rectangles, as we have like a really large number, this blue shaded region will become so small that we pretty much have an answer.